What if I told you that the universe has been racing away from itself for nearly 14 billion years, and right now, at this very moment, everything you can see is moving apart faster than you could ever imagine? What if I told you that galaxies billions of light years away are retreating from us at speeds that would make your head spin, and that this cosmic expansion is accelerating with each passing second? But here's the question that keeps cosmologists awake at night, the question that could determine the ultimate fate of everything that exists. When will it all stop? You've probably heard that the universe is expanding, but what you might not realize is just how mind-bendingly fast this expansion actually is. Right now, space itself is stretching at a rate of about 70 kilometers per second for every megaparsec of distance. That means a galaxy that's 10 megaparsecs away from us is moving away at 700 kilometers per second. A galaxy 100 megaparsecs away is racing away at 7,000 kilometers per second. And here's where it gets absolutely wild. There are galaxies so far away that they're moving away from us faster than the speed of light itself. Wait, didn't Einstein tell us that nothing can travel faster than light? Well, here's the thing. These galaxies aren't actually moving through space faster than light. Space itself is expanding, carrying those galaxies along for the ride. It's like standing on a moving walkway at the airport, except the walkway itself is stretching as you stand on it. The galaxies are just passengers on this cosmic conveyor belt of expanding space-time. But this raises an absolutely crucial question that most people never think to ask. If the universe has been expanding for almost 14 billion years, and if that expansion is actually speeding up, then what's going to happen next? Will this cosmic sprint continue forever, with galaxies racing away from each other until the universe becomes a cold, dark, empty void? Or is there some cosmic force that will eventually put on the brakes and bring everything back together? The answer to this question isn't just academic curiosity. It determines whether we live in a universe that will end in ice or fire, whether the stars will eventually burn out one by one until nothing remains, or whether everything will come crashing back together in a cosmic collision that would make the Big Bang look like a firecracker. Now, before we dive into the heart of this cosmic mystery, let me tell you why this matters more than you might think. Understanding when and how universal expansion might end isn't just about satisfying scientific curiosity, it's about understanding our place in the cosmic story, about knowing whether the universe we call home has an expiration date, and about grasping the ultimate destiny of every atom that makes up your body, every planet in our solar system, and every star in every galaxy you've ever seen twinkling in the night sky. The story of cosmic expansion begins with a discovery that completely revolutionized our understanding of the universe. In 1929, an astronomer named Edwin Hubble was studying distant galaxies using what was then the most powerful telescope in the world. He was measuring something called redshift, which is essentially cosmic Doppler effect. Just like the sound of an ambulance siren changes pitch as it moves toward or away from you, light from distant galaxies changes color as those galaxies move toward or away from us. What Hubble discovered was absolutely shocking. Nearly every galaxy he observed was redshifted, meaning they were all moving away from us. But here's the kicker. The farther away a galaxy was, the faster it was moving away. This wasn't random motion. This was a pattern, a cosmic choreography that revealed something profound about the nature of space itself. Imagine you're standing in the center of a balloon, and someone starts inflating it. Every point on the balloon's surface moves away from every other point, and the farther apart two points are, the faster they separate. That's exactly what Hubble discovered was happening to our universe. Space itself was expanding, carrying galaxies along like dots on the surface of an inflating balloon. This discovery led to one of the most important realizations in the history of science. If the universe is expanding now, then it must have been smaller in the past. Wind the cosmic clock backward far enough, and you reach a moment when everything in the universe was compressed into an infinitely small, infinitely dense point. This was the birth of the Big Bang theory, the idea that our universe began from a singular moment of explosive expansion nearly 14 billion years ago. But here's where the story gets even more interesting. For decades after Hubble's discovery, scientists assumed that this cosmic expansion would eventually slow down. After all, gravity is always pulling everything together, right? The gravitational attraction between all the matter in the universe should act like cosmic brakes, gradually slowing down the expansion until it eventually stops and reverses course. This led to three possible scenarios for the future of the universe. First, if there was enough matter in the universe, gravity would eventually overcome expansion, causing everything to collapse back together in what scientists called the Big Crunch. Second, if there wasn't quite enough matter, the universe would expand forever, but the expansion would slow down over time, eventually approaching zero but never quite stopping. Third, if the amount of matter was just right, the universe would expand forever at a gradually decreasing rate that would approach a constant value. These scenarios depended entirely on something called the critical density of the universe. Think of it like the escape velocity needed for a rocket to break free from Earth's gravity. If the universe has more than the critical density, gravity wins and everything eventually collapses. If it has less than the critical density, expansion wins and the universe expands forever. If it has exactly the critical density, you get a perfectly balanced universe that expands forever, but just barely. For years, scientists worked tirelessly to measure the actual density of the universe, counting up all the stars, gas, dust, and dark matter they could find. The results were puzzling. No matter how carefully they counted, they could only account for about 30% of the critical density needed to halt expansion. This suggested that we lived in an open universe, one that would expand forever with gradually slowing expansion. But then came 1998, a year that would change cosmology forever. Two independent teams of scientists were studying distant supernovae, using these cosmic explosions as standard candles to measure how the expansion rate of the universe has changed over time. What they found was so unexpected, so contrary to everything scientists believed about cosmic expansion, that they initially thought they had made a mistake. The expansion of the universe wasn't slowing down, it was speeding up. This discovery was like finding out that when you throw a ball up in the air, instead of slowing down due to gravity, it actually starts accelerating upward faster and faster. It violated everything scientists thought they knew about how the universe should behave. Gravity should be putting on the brakes, not pressing the accelerator. The only way to explain this accelerating expansion was to propose the existence of something completely new, something that had never been directly observed before. Scientists called it dark energy, and it makes up about 70% of everything in the universe. Unlike matter, which clumps together under its own gravitational attraction, dark energy seems to have the opposite effect. It pushes space apart, driving the acceleration we observe. Think of dark energy as a kind of cosmic anti-gravity. While regular matter and dark matter pull things together, dark energy pushes them apart. And here's the really mind-bending part. As the universe expands, the amount of matter and dark matter in any given volume of space decreases because the same amount of stuff is spread out over a larger volume. But dark energy appears to maintain a constant density even as space expands. This means that as the universe gets bigger, dark energy becomes more and more dominant. This discovery completely changed our understanding of the universe's fate. Instead of eventually slowing down and potentially reversing course, cosmic expansion is accelerating. Galaxies are moving away from us faster and faster with each passing moment. The universe we live in appears to be dominated by a mysterious force that will drive everything apart forever. But this raises an even more profound question. If dark energy continues to dominate, and if cosmic expansion continues to accelerate, what does that mean for the ultimate fate of everything we know? Will the stars eventually burn out one by one as galaxies drift so far apart that they can no longer interact? Will even atoms themselves be torn apart by the relentless stretching of space? The current best evidence suggests that we live in what cosmologists call a flat universe, one where the total density is very close to the critical density, but instead of being dominated by matter, our universe is dominated by dark energy. This has profound implications for when, if ever, cosmic expansion might come to an end. The implications of living in a dark energy-dominated universe are staggering beyond comprehension. Picture this scenario unfolding over cosmic timescales that make human history look like a brief flicker of candlelight. As dark energy continues its relentless push against the fabric of space itself, the universe will enter what scientists call the era of cosmic loneliness. Within the next 100 billion years, something remarkable and terrifying will happen. The expansion of space will accelerate to such a degree that distant galaxies will disappear beyond what astronomers call the cosmic horizon. Light from these galaxies will become so redshifted that it will fade into invisibility, stretched beyond the range of any possible detector. Future civilizations, if they exist, will look up at a night sky that contains only the stars and galaxies in their immediate cosmic neighborhood. But that's just the beginning of this cosmic transformation. The Milky Way and Andromeda galaxies are currently racing toward each other at about 250,000 miles per hour. and they're destined to collide in approximately 4.5 billion years. This galactic merger will create a massive elliptical galaxy that astronomers have already nicknamed Milkomeda. However, even this cosmic dance is temporary. As dark energy continues its work, eventually even the stars within Milkomeda will be separated by such vast distances that the night sky will become a sparse collection of isolated points of light. The really mind-blowing part comes when you consider what happens next. As the universe continues expanding and cooling, star formation will gradually cease. The raw materials needed to create new stars, primarily hydrogen and helium gas, will become so spread out that gravity can no longer pull them together into dense enough clumps to ignite nuclear fusion. The last generation of stars will burn through their fuel and die, leaving behind white dwarfs, neutron stars, and black holes as the only remnants of once brilliant stellar nurseries. This leads us to what cosmologists call the degenerate era, a period that will last for an almost incomprehensible length of time. During this era, which begins about 100 trillion years from now, the universe will be populated primarily by the cooling corpses of dead stars. White dwarf stars will slowly radiate away their remaining heat over trillions of years, eventually becoming cold, dark objects floating in an ever-expanding void. But even this isn't the end of the story. The expansion driven by dark energy becomes truly catastrophic when we consider what happens to the fundamental structure of space and time itself. There's a possibility, predicted by some models of dark energy, called the Big Rip scenario. In this nightmare version of cosmic evolution, dark energy doesn't just maintain a constant density as the universe expands. Instead, it actually grows stronger over time. If the Big Rip scenario is correct, then cosmic expansion will eventually accelerate so violently that it will overcome not just gravity, but all the fundamental forces that hold matter together. First, galaxy clusters will be torn apart as the space between galaxies expands faster than gravity can pull them together. Then individual galaxies will be shredded as the expansion overcomes the gravitational binding that holds their stars in orbit. The destruction doesn't stop there. Eventually, even solar systems will be dismantled as the space between planets expands faster than the gravitational influence of their parent stars. Then planets themselves will be ripped apart as expansion overcomes the electromagnetic forces that bind molecules together. In the final moments before the Big Rip, even atoms will be torn apart as space expands so rapidly that electrons can no longer maintain their orbits around atomic nuclei. The timeline for this cosmic catastrophe depends on the exact properties of dark energy, but some calculations suggest it could happen in as little as 22 billion years from now. That might sound like an impossibly long time, but remember that the universe is already nearly 14 billion years old. In cosmic terms, the Big Rip could be just around the corner. However, there's still enormous uncertainty about the true nature of dark energy and whether such extreme scenarios will actually unfold. Dark energy remains one of the biggest mysteries in modern physics. We know it exists because we can observe its effects on cosmic expansion, but we have no idea what it actually is, or whether its properties will remain constant over time. Some theories suggest that dark energy might not be a constant force. It could weaken over time, allowing gravity to eventually reassert its influence and potentially even reverse cosmic expansion. Other models propose that dark energy might be cyclical, growing stronger and weaker in patterns that could lead to a universe that expands and contracts in endless cycles. There's also the possibility that our understanding of dark energy is completely wrong. Maybe what we interpret as dark energy is actually a sign that our theories of gravity break down on cosmic scales. Perhaps there are extra dimensions of space that we haven't discovered yet. As Acceler and what we see aiding expansion is actually the result of gravitational effects leaking in from these hidden dimensions. The quest to understand dark energy has become one of the most important challenges in modern cosmology. Scientists are building increasingly sophisticated telescopes and detectors to study distant supernovae, map the large-scale structure of the universe, and measure tiny fluctuations in the cosmic microwave background radiation left over from the Big Bang. One of the most ambitious projects is the Vera Rubin Observatory, which will survey the entire visible sky every few nights for 10 years, creating the most detailed map of cosmic expansion ever attempted. By studying billions of galaxies and tracking how their distances change over time, scientists hope to determine whether dark energy is truly constant or whether it varies in ways that could change the ultimate fate of the universe. Meanwhile, space-based missions like the James Webb Space Telescope are peering deeper into cosmic history than ever before, observing galaxies as they appeared when the universe was just a fraction of its current age. These observations provide about how crucial data cosmic expansion has changed over the nearly 14 billion-year history of the universe. The stakes of this research couldn't be higher. Understanding the nature of dark energy isn't just about satisfying scientific curiosity, it's about determining whether we live in a universe with a finite lifespan or one that will continue expanding forever. It's about knowing whether the cosmic story has a definitive ending or whether it will continue writing itself across timescales that dwarf human imagination. But here's what makes this mystery even more intriguing. The question of when universal expansion might stop isn't just about the distant future. It's intimately connected to fundamental questions about the nature of reality itself. Why does dark energy exist at all? Why does it have the exact strength needed to dominate cosmic expansion without ripping apart local structures like galaxies and solar systems? Is there something special about the current epoch in cosmic history that makes us privileged observers of this cosmic acceleration? These questions touch on some of the deepest mysteries in physics and philosophy. They force us to confront the possibility that our universe might be just one of many, existing within a vast multiverse where different regions have different properties and different fates. They challenge us to consider whether the laws of physics themselves might evolve over time, or whether there are deeper principles governing the cosmos that we haven't yet discovered. The search for answers continues to drive some of the most exciting research in modern science, pushing the boundaries of our technology and our understanding of the fundamental nature of reality itself. What makes this cosmic detective story even more fascinating is that dark energy might not be the unchanging force that scientists initially assumed. Recent observations have started to reveal subtle variations in how cosmic expansion has evolved over the universe's 14 billion-year history, and these variations could hold the key to predicting when, if ever, the expansion might finally come to an end. Think about it this way. When you're driving down a highway and you press the accelerator, your speedometer shows you're going faster. But if you want to know what's going to happen next, you need to know whether your foot is still pressing down on that accelerator, whether you're easing up, or whether you're about to hit the brakes. The same principle applies to cosmic expansion. We know the universe is accelerating, but the crucial question is whether that acceleration is constant, increasing, or potentially even beginning to slow down. This is where things get really interesting, because the answer depends on something called the equation of state of dark energy. Now, before your eyes glaze over at the technical terminology, let me explain what this actually means in simple terms. The equation of state is basically a mathematical description of how dark energy behaves under different conditions. It tells us whether dark energy maintains a constant density as the universe expands, or whether it becomes stronger or weaker over time. If dark energy has what physicists call a constant equation of state, with a value of -1, then it behaves exactly like Einstein's cosmological constant. In this scenario, dark energy maintains a perfectly constant density throughout all of space and time, which means cosmic expansion will continue accelerating forever at an ever-increasing rate. The universe will expand exponentially, doubling in size at regular intervals until everything we can currently observe disappears beyond the cosmic horizon. But here's where the story takes a potentially dramatic turn. Recent measurements from cutting-edge telescopes and space missions have begun to suggest that dark energy might not have a constant equation of state after all. Some observations hint that the equation of state might be slightly different from -1, which would mean dark energy could be evolving over time. If dark energy is actually growing stronger as the universe ages, then we're heading toward that big rip scenario I mentioned earlier, where cosmic expansion eventually becomes so violent that it tears apart galaxies, stars, planets, and even atoms themselves. But if dark energy is gradually weakening, then something absolutely extraordinary could happen. The universe might eventually enter a phase where gravity begins to reassert its influence, potentially leading to a scenario where cosmic expansion slows down, stops, and even reverses. This possibility has led to one of the most intriguing concepts in modern cosmology, something called the Big Crunch. Picture the entire history of cosmic expansion playing in reverse. Galaxies that are currently racing away from each other would begin moving closer together. The cosmic microwave background radiation, which is currently cooling as the universe expands, would start heating up as space contracts. In a Big Crunch scenario, the universe would literally collapse back on itself, with all the matter and energy that spread out during 14 billion years of expansion eventually coming back together in a cosmic implosion that would be the mirror image of the Big Bang. Temperatures would rise as space contracted, stars would merge, and eventually everything would be compressed back into the infinitely dense, infinitely hot state from which the universe originally emerged. But the Big Crunch scenario raises mind-bending questions about what happens next. Does the cosmic story end there, with everything crushed out of existence? Or does the universe bounce back, triggering a new Big Bang and beginning the cycle all over again? Some theories suggest that we might live in a cyclic universe, one that expands and contracts in an endless rhythm that has been repeating for an eternity of cosmic cycles. The cyclic universe model is particularly fascinating because it offers a potential solution to some of the biggest puzzles in cosmology. It could explain why the universe appears to be fine-tuned for the existence of stars, planets, and life. Instead of requiring special initial conditions that somehow produced our life-friendly cosmos, a cyclic universe would have had unlimited opportunities to explore different configurations until it stumbled upon one that could support complex structures. However, determining which of these scenarios actually describes our cosmic future requires incredibly precise measurements of how dark energy behaves over vast scales of space and time. This is where modern astronomy is pushing the absolute limits of what's technologically possible. Scientists are using techniques that would have seemed like pure science fiction just a few decades ago. One of the most powerful approaches involves studying something called baryon acoustic oscillations, which are essentially fossilized sound waves from the early universe. In the first few 100,000 years after the Big Bang, when the universe was still hot and dense, sound waves rippled through the cosmic plasma like waves in a pond. When the universe finally cooled enough for atoms to form, these sound waves were frozen in place, creating subtle patterns in how matter is distributed throughout the cosmos. By measuring these patterns in the positions of millions of galaxies, scientists can reconstruct the expansion history of the universe with extraordinary precision. It's like being a cosmic archaeologist, using the fossil remains of ancient sound waves to understand how the universe has evolved over nearly 14 billion years of cosmic time. Another crucial piece of evidence comes from studying Type 1 supernovae, which are among the most violent and luminous explosions in the universe. These stellar detonations are so bright that they can be seen from billions of light years away, and they serve as cosmic lighthouses that allow scientists to measure distances and expansion rates across vast reaches of space and time. What makes Type 1 supernovae particularly valuable is that they all have approximately the same intrinsic brightness, which means scientists can use them as standard candles to measure cosmic distances. By comparing how bright these supernovae appear from Earth with how bright they should be based on their distance, astronomers can determine how much the universe has expanded since the light left these distant stellar explosions. The data from these cosmic lighthouses has revealed something absolutely remarkable. The expansion rate of the universe has not been constant throughout cosmic history. Instead, it went through a dramatic transition approximately 5 billion years ago, right around the time our solar system was forming. Before that transition, cosmic expansion was actually decelerating, slowing down under the gravitational influence of matter and dark matter. After the transition, expansion began accelerating as dark energy took control. This discovery has profound implications for understanding when cosmic expansion might end. If dark energy only recently became dominant, and if its properties are still evolving, then the future of the universe might be very different from what we would predict based on current expansion rates alone. Some scientists have proposed that dark energy might be cyclical, growing stronger and weaker over time scales of hundreds of billions of years. In this scenario, we might currently be living through a temporary phase of acceleration that will eventually give way to a new period of deceleration. The universe could be like a cosmic pendulum, swinging between phases of expansion and contraction over time scales that make the current age of the universe seem like a brief moment. Other researchers have suggested that dark energy might be connected to quantum effects that operate on the largest scales in the universe. According to quantum mechanics, even empty space is filled with virtual particles that constantly pop into existence and disappear again. These quantum fluctuations might contribute to the energy density of space itself, providing a physical mechanism for dark energy that could evolve as the universe ages and cools. The quantum vacuum approach to dark energy is particularly intriguing because it suggests that the expansion of the universe might be intimately connected to the fundamental structure of reality at the smallest possible scales. If this is true, then understanding when cosmic expansion will end might require a complete theory of quantum gravity, one that successfully unifies general relativity with quantum mechanics, us to one. This brings of the most ambitious goals in modern physics, the search for a theory of everything that can explain all the fundamental forces and particles in the universe within a single mathematical framework. String theory, loop quantum gravity, and other approaches to quantum gravity all make different predictions about how space and time behave under extreme conditions, and these differences could have observable consequences for the future evolution of cosmic expansion. The stakes of this research extend far beyond academic curiosity. Understanding the ultimate fate of the universe forces us to confront fundamental questions about the nature of existence itself. Are we living in a universe with a finite lifespan, destined to end in heat death, cosmic collapse, or violent destruction? Or does the cosmic story continue indefinitely, with new chapters being written across timescales that dwarf human imagination? These questions also have profound implications for how we understand our place in the cosmic order. If the universe will expand forever, then the matter that makes up your body, the Earth, and everything you've ever known will eventually be scattered across impossible distances, with each atom separated from every other atom by vast gulfs of empty space. If the universe will eventually collapse, then all of cosmic history, including every human achievement and every moment of consciousness, will ultimately be compressed back into the primordial fireball from which it all began. But perhaps the most remarkable aspect of this cosmic mystery is that we're living at exactly the right time in cosmic history to observe and study it. Dark energy has only recently become dominant, which means we can still see the effects of the transition from deceleration to acceleration in our observations of distant galaxies and supernovae. If we had evolved a few billion years earlier, dark energy would have been too weak to detect. If we had evolved a few billion years later, distant galaxies would already have disappeared beyond the cosmic horizon. This cosmic timing raises profound questions about whether our existence is somehow connected to the properties of dark energy itself. Some scientists have proposed anthropic arguments suggesting that the strength of dark energy must be fine-tuned to allow the formation of stars, galaxies, and ultimately life. If dark energy were much stronger, it would have prevented the formation of large-scale structures in the early universe. If it were much weaker, the universe would have collapsed before stars could form and evolve. The anthropic principle suggests that we observe the particular value of dark energy that we do precisely because we exist to observe it. In a multiverse containing regions with different values of dark energy, only those regions with the right properties would evolve conscious observers capable of studying cosmic expansion. This idea is both compelling and controversial, as it suggests that the fundamental constants of physics might be determined by the requirement that life can exist to measure them. Regardless of whether anthropic arguments provide valid explanations for cosmic properties, the fact remains that we are privileged observers of one of the most dramatic transitions in cosmic history. We're witnessing the moment when dark energy takes control of the universe's fate, potentially determining whether cosmic expansion continues forever or eventually comes to an end. The tools we're using to study this transition are becoming more sophisticated every year. Ground-based telescopes like the Extremely Large Telescope, currently under construction in Chile, will be able to observe galaxies and supernovae with unprecedented precision, potentially revealing subtle changes in dark energy properties over cosmic time. Space-based missions like the Nancy Grace Roman Space Telescope will survey billions of galaxies, creating three-dimensional maps of cosmic structure that span nearly the entire observable universe. These observations will help scientists determine whether dark energy truly has a constant equation of state, or whether it's evolving in ways that could change the ultimate destiny of everything that exists. The data might reveal that we're heading toward eternal expansion, cyclical evolution, or catastrophic collapse, but whatever the answer turns out to be, it will represent one of the most important discoveries in the history of human knowledge. The question of when the universe will stop expanding touches on the deepest mysteries of existence, from the nature of space and time to the origin of physical laws themselves. It challenges us to think beyond the scales of human experience and consider the ultimate fate of every atom, every star, and every galaxy in the cosmic web that surrounds us. As we stand on the precipice of these cosmic revelations, there is something absolutely extraordinary happening right now that most people don't realize. The universe isn't just expanding in some abstract theoretical way that only affects distant galaxies billions of light years away. It's expanding right here, right now, in the space between your atoms, in the gap between Earth and the Moon, in the distance between our solar system and the nearest star. But here's what will blow your mind. The expansion is so subtle on small scales that the electromagnetic forces holding your atoms together, the gravitational pull keeping you planted on Earth's surface, and even the gravity binding our solar system completely overpower cosmic expansion. It's like trying to stretch a steel cable with your bare hands. The local forces are so much stronger that expansion becomes completely negligible. This creates one of the most fascinating puzzles in modern cosmology. How can something be simultaneously unstoppable on cosmic scales yet completely imperceptible on human scales? The answer lies in understanding the true nature of what we call dark energy, and it reveals something profound about how the universe operates on different levels of reality. Think of it this way. Imagine you're standing in a river where the current is flowing downstream, but you're strong enough to swim upstream against that current. On a small scale, your swimming completely overcomes the river's flow, but step back and look at the entire river system, and you'll see that the current is carrying enormous amounts of water downstream, regardless of your individual swimming efforts. The river doesn't care about your local resistance to its flow. That's exactly what's happening with cosmic expansion. Locally, gravity and other fundamental forces create bound systems like atoms, planets, solar systems, and even entire galaxies that resist expansion. These structures swim upstream against the cosmic current, maintaining their integrity despite the universe's relentless stretching. But on the largest scales, where the distances between galaxy clusters are so vast that gravitational bonds become weak, dark energy wins decisively. This scale-dependent behavior of cosmic expansion leads to some truly mind-bending consequences for the future. As dark energy continues its work, the universe will gradually segregate itself into isolated islands of matter floating in an ever-expanding ocean of empty space. Galaxy clusters will become cosmic archipelagos, separated by distances so vast that light traveling between them will be stretched beyond recognition. Within these island universes, however, life could potentially continue for trillions upon trillions of years. Stars will keep shining, planets will keep orbiting, and if intelligent civilizations survive, they'll witness their observable universe gradually shrinking as distant galaxies disappear beyond the cosmic horizon. Future astronomers in these island universes might conclude that their galaxy cluster represents the entirety of existence, just as astronomers a century ago believed the Milky Way was the entire universe. But even these cosmic islands aren't permanent refuges from the effects of expansion. As we venture deeper into the far future, something called proton decay might ultimately determine when the last chapter of the cosmic story gets written. According to some theories in particle physics, even protons, the building blocks of atomic nuclei, aren't completely stable over extremely long time periods. If protons do indeed decay, then every atom in the universe has an expiration date. The hydrogen in your body, the carbon that forms the backbone of organic molecules, the oxygen you breathe, all of it will eventually disintegrate into lighter particles and energy. The timescale for this process is almost incomprehensibly long, with protons having a half-life of at least 10 to the 34th years, but it represents the ultimate endpoint of material existence. This brings us to what cosmologists call the black hole era, a period in the far future when black holes will be the dominant objects in the universe. After all the stars have burned out, after all the protons have decayed, black holes will remain as the last massive structures in an increasingly empty cosmos. These gravitational monsters will slowly evaporate through a process called Hawking radiation, taking an almost unimaginable amount of time to completely disappear. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate completely. Supermassive black holes like the one at the center of our galaxy would require 10 to the 100 years to fade away entirely. These numbers are so large that they make the current age of the universe seem like a brief instant by comparison. Yet even this isn't the end of the story, because the evaporation of black holes through Hawking radiation represents one of the most beautiful and mysterious connections between gravity, thermodynamics, and quantum mechanics. As a black hole shrinks, it actually gets hotter and radiates energy faster, like a cosmic pressure cooker releasing steam. In its final moments, a black hole will explode with the energy of millions of hydrogen bombs, converting its remaining mass into a burst of elementary particles and radiation. When the last black hole finally evaporates, the universe will enter what physicists call the photon era, a time when the cosmos will be filled with nothing but elementary particles, photons, and the quantum vacuum itself. The temperature of space will approach absolute zero, and the density of matter will be so low that particles might travel for billions of years without ever encountering another particle. But here's where quantum mechanics introduces an element of genuine mystery into the far future of cosmic expansion. According to quantum theory, even the vacuum of empty space isn't truly empty. It's filled with quantum fluctuations, virtual particles that constantly pop into existence and disappear again on timescales so brief that they normally can't be observed directly. These quantum fluctuations might seem insignificant, but over the vast timescales we're discussing, they could lead to some truly extraordinary phenomena. There's a theoretical possibility, for instance, that quantum fluctuations could spontaneously create new particles, new energy, and even new universes within the expanding void of our dying cosmos. One of the most mind-boggling predictions involves something called quantum tunneling on cosmic scales. Just as quantum particles can tunnel through barriers that should be impossible to cross according to classical physics, the entire universe might be able to quantum tunnel from its current state into a completely different configuration. This could happen spontaneously, without any external cause, driven purely by the probabilistic nature of quantum mechanics. If cosmic-scale quantum tunneling occurs, it could completely reset the expansion history of the universe. The vacuum of space might suddenly decay into a lower energy state, releasing enormous amounts of energy and potentially triggering a new phase of cosmic inflation. This would be like hitting a cosmic reset button, erasing the current phase of dark energy-dominated expansion and beginning an entirely new chapter in the universe's evolution. The probability of such an event is extraordinarily small on human timescales, but given infinite time, even the most improbable quantum events become inevitable. This means that no matter how certain we are about the future trajectory of cosmic expansion based on current observations, quantum mechanics introduces an element of fundamental uncertainty that could change everything. This quantum uncertainty extends to the nature of dark energy itself. Some theories suggest that dark energy might not be a fundamental constant of nature, but rather a temporary feature of our current cosmic epoch that could spontaneously change through quantum processes. If dark energy is actually a quantum field that exists in a metastable state, it might eventually decay into a more stable configuration, completely altering the expansion dynamics of the universe. The decay of dark energy could lead to scenarios even more dramatic than the Big Crunch. Instead of a gradual reversal of cosmic expansion, the universe might undergo a phase transition so violent that it would instantly destroy every structure that has ever existed. Alternatively, the decay might trigger a new period of cosmic inflation, stretching space so rapidly that our entire observable universe would become a tiny speck within a much larger and fundamentally different cosmos. These possibilities highlight one of the most profound aspects of the expansion question. Even if we develop a complete understanding of dark energy and can predict its behavior with perfect accuracy based on current physics, we still can't be certain about the ultimate fate of cosmic expansion because our understanding of physics itself might be incomplete. The history of science is filled with examples of theories that seemed complete and final, only to be revolutionized by new discoveries that revealed deeper layers of reality. Newton's laws of motion seemed to provide a complete description of how objects move, until Einstein showed that space and time themselves are dynamic and curved by matter and energy. Einstein's general relativity seemed to provide a complete description of gravity, until quantum mechanics revealed that reality is fundamentally probabilistic at the smallest scales. We might currently be in a similar position with respect to dark energy and cosmic expansion. Our current theories might provide an accurate description of what we can observe today, but they might miss crucial aspects of reality that will only become apparent as our understanding deepens and our observational capabilities improve. This is why the question of when the universe will stop expanding remains so tantalizingly open-ended. It's not just a matter of making better measurements of dark energy's properties, though that's certainly important. It's also about discovering whether there are deeper principles governing the cosmos that we haven't yet imagined. The search for these deeper principles is driving some of the most ambitious experiments and observations ever attempted. Scientists are building gravitational wave detectors that can sense ripples in space-time caused by cosmic events billions of years ago. They're constructing particle accelerators that recreate conditions similar to those that existed in the first fraction of a second after the Big Bang. They're launching space telescopes that can peer deeper into cosmic history than ever before possible. Each of these efforts is designed and potentially reveal new phenomena to test our current understanding of physics. There's no reason to believe that we have dark energy itself that could change our predictions about cosmic expansion. The discovery came as a completologists and have uncovered all the surprise to most cosmises the universe has in store. In fact, some of the most exciting possibilities involve scenarios where cosmic expansion doesn't simply continue or reverse, but transforms into something completely different that we haven't yet learned to imagine. The universe might transition into higher dimensional configurations that our three-dimensional minds can't properly visualize. It might spawn child universes through quantum processes that create new domains, might even participate in interactions of space and time. It with other universes in a vast multiverse system where expansion and contraction are just local phenomena within a much grander cosmic structure. These speculative possibilities remind us that the question of when cosmic expansion will end is intimately connected to some of the deepest mysteries about the nature of reality itself. Understanding the ultimate fate of the universe requires understanding the fundamental structure of space, time, matter, and energy at levels that push the absolute limits of human knowledge and imagination. Yet despite these vast uncertainties, there's something profoundly meaningful about humanity's attempt to understand cosmic expansion and its ultimate destiny. We're a species that emerged from cosmic dust, achieved consciousness, developed science, and now contemplates the fate of the very universe that gave us birth. The atoms in our bodies were forged in the cores of dying stars, scattered by supernova explosions, and eventually assembled into living beings capable of wondering about their cosmic origins and destiny. The fact that the universe has evolved conscious observers capable of studying cosmic expansion might itself be a crucial clue about the ultimate answer to our question. If the universe is destined for eternal expansion into a cold, empty void, why did it bother to create beings capable of understanding and lamenting that fate? If cosmic expansion will eventually reverse into a big crunch, why did consciousness emerge at precisely the moment when dark energy is taking control? These questions touch on some of the deepest philosophical issues in science and human existence. They force us to consider whether consciousness and intelligence play any fundamental role in cosmic evolution, or whether we're simply temporary accidents in an indifferent universe that will continue its expansion regardless of our presence or understanding. The answers to these questions might ultimately depend we haven't yet understood on discoveries we haven't yet made, principles and observations we haven't yet been able to perform. But the very fact that we can ask these questions, that we can contemplate the ultimate fate of everything that exists, represents something remarkable about the cosmic story we're all part of. As we continue pushing the boundaries of our knowledge about dark energy, cosmic expansion, and the ultimate fate of the universe, we're not just satisfying scientific curiosity, we're participating in one of the most profound adventures in the history of conscious thought, an attempt to understand our place in a cosmos whose scale, complexity, and ultimate destiny continue to exceed our wildest imaginations. The search for answers about cosmic expansion has led scientists to explore some of the most exotic and mind-bending phenomena in the universe. Consider this remarkable fact. Right now, there are experiments running deep underground, in abandoned mines and specially constructed laboratories that are trying to directly detect dark matter particles as they stream through your body at this very moment. These experiments represent humanity's attempt to understand the invisible scaffolding that shapes cosmic expansion. Dark matter, which makes up about 25% of the universe, doesn't interact with light or ordinary matter in ways we can easily observe. But it does interact gravitationally, and its presence has been crucial in determining how cosmic structures formed and evolved over billions of years. What makes this particularly fascinating is that the balance between dark matter and dark energy has been shifting throughout cosmic history, and this shift directly impacts when and how cosmic expansion might eventually end. In the early universe, dark matter was the dominant force shaping cosmic evolution. It provided the gravitational seeds that allowed gas clouds to collapse and form the first stars and galaxies. Without dark matter, the universe would have remained a smooth, featureless expanse of hydrogen and helium gas, never developing the complex structures we see today. But as the universe expanded and dark matter became more diluted, dark energy began to assert its influence. This transition represents one of the most dramatic phase changes in cosmic history, comparable to the moment when water turns to steam or when a solid becomes a liquid. The universe literally shifted from one type of behavior to another, and we're still living through the consequences of that transition. Understanding this transition is crucial because it might not be permanent. Some theories suggest that dark energy itself might be temporary, a phase that the universe is passing through on its way to something completely different. Just as water can exist as ice, liquid, or vapor depending on temperature and pressure, the vacuum of space might be able to exist in different states depending on cosmic conditions that change over time. This possibility leads to one of the most intriguing scenarios for the future of cosmic expansion. Instead of continuing forever or reversing into a big crunch, the universe might undergo what physicists call a false vacuum decay. This would be like discovering that what we thought was the ground floor is actually just a mezzanine, and there are deeper levels of reality waiting to be explored. If false vacuum decay occurs, it would propagate outward from its point of origin at the speed of light, creating an expanding bubble of space with completely different physical properties. Inside this bubble, the fundamental constants of nature might be different. The strength of gravity, the mass of particles, even the number of spatial dimensions could be altered in ways that would make our current universe unrecognizable. The truly unsettling aspect of false vacuum decay is that it could happen anywhere, at any time, without warning. There would be no way to detect it approaching because the boundary of the expanding bubble travels at light speed, which means no information about its existence could reach us until it was already here. One moment you're reading about cosmic expansion, and the next moment the fundamental nature of reality has completely changed. But before you lose too much sleep over this possibility, remember that the probability of false vacuum decay occurring in any given century, or even any given million years, is extraordinarily small. The universe has been stable for nearly 14 billion years, which suggests that if we are living in a false vacuum, it's a very stable one that could persist for timescales much longer than the current age of the cosmos. This stability question brings us back to one of the central mysteries of dark energy. Why does it have exactly the strength it does? If dark energy were just slightly stronger, it would have prevented the formation of galaxies and stars. If it were slightly weaker, the universe would have collapsed long before life could evolve. The fact that dark energy has just the right strength to allow complex structures while still dominating cosmic expansion is one of the most puzzling coincidences in all of physics. Some scientists argue that this apparent fine-tuning is evidence for the existence of a multiverse, a vast ensemble of universes with different physical properties. In this scenario, we observe the particular strength of dark energy that we do because we happen to live in one of the rare universes where conditions are just right for the existence of observers like ourselves. The multiverse hypothesis is both elegant and deeply troubling from a scientific perspective. It's elegant because it explains why our universe seems so perfectly calibrated for the existence of complexity and life. But it's troubling because it might be fundamentally untestable. If there are infinite universes with different properties, and we can only observe our own, then the multiverse hypothesis might be more philosophy than science. However, some researchers have proposed ways that evidence for a multiverse might show up in observations of cosmic expansion. If our universe occasionally collides or interacts with neighboring universes, these encounters might leave subtle imprints in the cosmic microwave background radiation or in the large-scale distribution of galaxies. Finding such evidence would revolutionize our understanding not just of cosmic expansion, but of the fundamental nature of existence itself. The search for multi-hosulative Butterverse signatures become one of the most potentially revolutionary areas of modern cosmology. Scientists are analyzing data from spaced cosmic surveys, telescopes, and looking for patterns that might indicate odd by external universe has been influence factors beyond the standard model of cosmology. Meanwhile, theoretical physicists are developing increasingly sophisticated models of how universes might form, interact, and evolve within a larger multiverse framework. These models make specific predictions about how cosmic expansion should behave if we're part of a larger ensemble of universes, predictions that might eventually be testable with future observations. The implications of living in a multiverse would be profound for understanding when cosmic expansion might end. If universes can spawn other universes through quantum processes, then the end of expansion in our particular cosmic domain might simply mark the beginning of new expansion phases in daughter universes. The cosmic story wouldn't end with heat death or collapse, but would continue indefinitely through an eternal process of cosmic reproduction. This eternal inflation scenario suggests that while our observable end for a universe might be destined particular fate, the larger multiverse of which we're part could continue expanding and evolving forever. New universes would constantly be born, each with its own expansion history and ultimate destiny, creating a fractal structure of nested cosmoses extending infinitely in space and time. But even if we don't live in a multiverse, the question of cosmic expansion's ultimate fate remains intimately connected to discoveries waiting to be made in fundamental physics. The next generation of particle accelerators might reveal new particles or forces that could alter our understanding of dark energy. Advances in quantum gravity theory might show that space and time themselves have properties we haven't yet discovered that could change cosmic expansion in unexpected ways. One particularly intriguing possibility involves the relationship between information and cosmic expansion. Some theories suggest that the universe might be fundamentally computational in nature, with space and time emerging from underlying information processing. If this is true, then cosmic expansion might be governed by principles more similar to computer science than traditional physics. In an information-based universe, the question of when expansion stops might depend on factors like computational capacity, information density, and processing speed, rather than just matter, energy, and space-time geometry. The universe might expand as long as it has sufficient computational resources to support increasing complexity, or it might contract when information processing reaches certain limits. These like science fiction, but their taken ideas might sound seriously by researchers. The intersection of physics, computer science, working at and information theory. The discovery that black holes have entropy proportional to their surface area rather than their volume suggests that information plays a more fundamental role in physics than previously imagined. If information is indeed fundamental to cosmic evolution, then conscious observers like ourselves might play a more important role in determining the universe's fate than we've traditionally assumed. The act of observation and measurement might not just reveal the properties of cosmic expansion, but might actually influence those properties through quantum mechanical effects that operate on cosmic scales. This brings us full circle to one of the most profound aspects of the expansion question. We're not just passive observers trying to predict the fate of an indifferent universe. We're active participants in cosmic evolution, conscious beings whose very existence might be connected that determine whether expansion to the fundamental processes continues forever or eventually comes to an end. The universe has spent nearly 14 billion years evolving from a hot, dense state to the complex cosmos we observe today. It has created stars that forge heavy elements, planets that can support life, and conscious beings capable of contemplating cosmic destiny. Whether this represents a meaningful progression towards some ultimate purpose, or simply a temporary fluctuation in an otherwise pointless expansion, remains one of the deepest questions we can ask. As we stand at this unique moment in cosmic history, when dark energy has just begun to dominate but distant galaxies are still visible, we have an unprecedented opportunity to study the forces that will determine the ultimate fate of everything that exists. The telescopes we're building, the experiments we're conducting, and the theories we're developing might provide the final answer to when, if ever, the universe will stop expanding. But regardless of what of understanding cosmic expansion has we discover, the journey already revealed something remarkable about the universe and our place within it. We are conscious patterns in the cosmic web, temporary arrangements of matter and energy that have achieved the ability to contemplate their own origins and destiny. In asking when the universe will stop expanding, we're participating in the cosmos coming to know itself. The answer to that question might be hiding in plain sight, encoded in the very fabric of reality itself, waiting for the right combination of technology and insight to reveal its secrets. But here's what makes this cosmic mystery even more mind-bending. The tools we're using to study expansion aren't just telescopes and equations. They're time machines. Every time astronomers look at a distant galaxy, they're seeing it as it existed millions or billions of years ago, when its light first began the long journey to Earth. This means we can literally watch the history of cosmic expansion unfold by studying objects at different distances. A galaxy 10 million light-years away shows us how expansion was behaving 10 million years ago. A galaxy 10 billion light-years away shows us expansion as it was when the universe was less than 4 billion years old. This cosmic archaeology has revealed something absolutely extraordinary about the nature of time itself in an expanding universe. The expansion isn't just stretching space between galaxies, it's stretching time as well. Events that occurred in the early universe appear to unfold in slow motion when viewed from our current cosmic epoch, like watching a movie that's been slowed down by the expansion of the medium it's recorded on. Think about what this means for understanding when expansion might end. We're not just dealing with distances and velocities. We're dealing with the fundamental nature of temporal flow in a universe where time itself is being stretched by the same forces that drive galaxies apart. The question of when expansion stops becomes intertwined with questions about the nature of time that philosophers and physicists have grappled with for centuries. This temporal stretching creates one of the most beautiful and haunting aspects of cosmic expansion. Light from the most distant observable galaxies has been traveling toward us for so long that those galaxies might not even exist anymore. We're seeing their ancient past, frozen in light that has been journeying through expanding space for most of the universe's history. By the time this light reaches us, those distant stellar cities might have evolved beyond recognition, or they might have been torn apart by the very expansion that allowed their light to reach us. The cosmic microwave background radiation, the afterglow of the Big Bang itself, has been traveling toward us for nearly 14 billion years. When this radiation was first emitted, the entire observable universe was smaller than our solar system is today. The photons that make up this ancient light have been stretched by cosmic expansion from high-energy gamma rays to low-energy microwaves, carrying with them a fossil record of the universe's infancy. Studying this ancient light has revealed something that challenges our intuition about cosmic expansion. The early universe was actually much denser and hotter than simple expansion models would predict. This discovery led to the theory of cosmic inflation, the idea that the universe underwent a brief but incredible period of exponential expansion in its first fraction of a second of existence. During inflation, space expanded faster than light itself, stretching quantum fluctuations to macroscopic scales and creating the tiny density variations that would eventually grow into galaxies, stars, and planets. This primordial expansion was driven by a form of energy similar to dark energy, but billions of times more powerful. The inflationary epoch ended almost as suddenly as it began, transitioning into the more sedate expansion that characterized most of cosmic history until dark energy recently took control. The connection between primordial inflation and current dark energy acceleration suggests that the universe might have a tendency toward phases of rapid expansion separated by periods of more gradual growth. If this pattern continues, our current phase of dark energy dominance might not be permanent. The universe could be building toward another inflationary episode that would completely reset cosmic expansion and begin a new chapter in the cosmic story. This cyclical possibility raises profound questions about the nature of cosmic time and causality. If the universe undergoes repeated cycles of expansion, inflation, and renewal, then the concept of a final endpoint to expansion becomes meaningless. Instead of asking when expansion will stop, we might need to ask how many expansion cycles the universe has already experienced, and what determines the transition between different phases of cosmic evolution. Some theories suggest that we might be able to find evidence of previous expansion cycles encoded in the cosmic microwave background or in the large-scale structure of the universe. These signatures would appear as subtle patterns that couldn't be explained by a single Big Bang event, but would make perfect sense if our universe had undergone multiple episodes of expansion and renewal. The search for these cyclic signatures has become one of the most exciting frontiers in observational cosmology. Scientists are developing increasingly sensitive instruments capable of detecting the faintest traces of cosmic history, looking for clues that might reveal whether we're living through the first iteration of cosmic expansion or just the latest episode in an eternal cycle. But even if we discover evidence for cosmic cycles, the question of ultimate endpoints remains. Do these cycles continue forever, with no beginning or end? or do they eventually wind down or build up to some final state that represents the true conclusion of cosmic evolution? The answer might depend on whether the laws of physics themselves evolve over cosmic time, or whether they remain constant across all cycles of expansion and renewal. Recent discoveries in particle physics suggest that what we consider fundamental constants might not be constant at all. The fine structure constant, which determines the strength of electromagnetic interactions, might have been slightly different in the early universe. If fundamental constants can change over cosmic time, then the behavior of dark energy and cosmic expansion might also evolve in ways we haven't yet considered. This variability of physical constants opens up entirely new possibilities for the future of cosmic expansion. Instead of following predictable trajectories based on current physics, the universe might transition through phases governed by entirely different sets of physical laws. Dark energy could strengthen or weaken depending on how fundamental constants evolve, leading to scenarios where expansion accelerates, decelerates, or transforms into something completely different. The evolution of physical constants also suggests that consciousness and intelligence might play a more active role in cosmic evolution than we've traditionally assumed. If the universe is capable of fine-tuning its own properties over time, then the emergence of observers capable of studying and potentially influencing those properties might represent a crucial phase transition in cosmic evolution. This idea leads to some of the most speculative but fascinating possibilities for the future of expansion. Advanced civilizations, given enough time and technological development, might eventually gain the ability to influence cosmic expansion directly. They might learn to manipulate dark energy, create artificial gravity fields, or even engineer transitions between different vacuum states that could reset the expansion history of local regions of space. If such capabilities are possible, then the question of when cosmic expansion stops might ultimately be answered not by passive observation of natural processes, but by active intervention from conscious beings who choose to shape the universe's destiny according to their own purposes and values. The cosmos might evolve from a purely physical system governed by impersonal laws into something more resembling a designed artifact created by intelligence that has learned to master the fundamental forces of nature. This possibility raises profound questions about the relationship between mind and cosmos that go far beyond traditional physics and astronomy. If intelligence can eventually influence cosmic expansion, then consciousness might not be an accidental byproduct of cosmic evolution, but rather its ultimate purpose. The universe might be in the process of awakening to itself through the emergence of conscious observers who will eventually become active participants in cosmic engineering. But even without invoking such speculative scenarios, the current trajectory of cosmic expansion research is revealing connections between mind and cosmos that previous generations of scientists could never have imagined. The quantum mechanical nature of reality means that observation and measurement play fundamental roles in determining physical outcomes, and these effects might operate on cosmic scales in ways we're only beginning to understand. The act of studying cosmic expansion might itself influence the phenomenon we're trying to understand. If consciousness and measurement play active roles in quantum mechanics, and if quantum effects operate on cosmic scales, then our attempts to determine when expansion will stop might actually influence when and how it stops. We might be participating in a cosmic feedback loop where observers and observed are inextricably connected in ways that make prediction and control indistinguishable. This quantum connection between consciousness and cosmic evolution suggests that the ultimate answer to our question might not be found through passive observation alone, but through active engagement with the universe as conscious participants in its ongoing evolution. The search for answers about cosmic expansion becomes not just a scientific endeavor, but a form of cosmic dialogue between mind and nature that could ultimately determine the fate of both. As we develop more sophisticated ways of studying dark energy and cosmic expansion, we're also developing new ways of thinking about the relationship between knowledge and reality. The universe we're studying is not separate from the minds that study it. We are patterns of organized matter and energy that have emerged from cosmic evolution and achieved the ability to contemplate the very processes that created us. This self-referential aspect of cosmic research creates fascinating paradoxes that challenge traditional notions of scientific objectivity. We're using brains made of atoms forged in stellar cores to study the expansion of the space that contains those stars. We're employing mathematical concepts developed by conscious minds to understand the physical processes that gave rise to consciousness itself. The resolution of these paradoxes might hold the key to understanding not just when cosmic expansion will stop, but why it began in the first place. If mind and cosmos are more intimately connected than we've traditionally assumed, then the emergence of consciousness might represent a crucial phase transition in cosmic evolution, one that fundamentally alters the trajectory of expansion and potentially determines its ultimate fate. The implications of this mind-cosmos connection extend far beyond academic speculation. If consciousness plays an active role in cosmic evolution, then the choices we make as individuals and as a species might have consequences that extend far beyond Earth and far into the future. Our decisions about how to use technology, how to treat our environment, and how to relate to each other might influence the ultimate destiny of cosmic expansion itself. This possibility transforms the question of when the universe will stop expanding from a purely scientific inquiry into a moral and existential challenge. We might not just be observers trying to predict the universe's fate, but active participants whose choices help determine that fate. The universe might stop expanding when conscious beings decide to stop it, or it might continue forever if we choose to let it run its natural course. The search for answers about cosmic expansion thus becomes inseparable from the search for answers about consciousness, purpose, and meaning in a universe that has evolved the capacity to contemplate its own existence. We are the universe asking questions about itself, and the answers we find might ultimately depend as much on who we choose to become as on what we manage to discover about dark energy and space-time geometry. As our instruments become more sensitive and our theories more sophisticated, we're approaching a moment in cosmic history when these profound questions might finally receive definitive answers. The next few decades could witness discoveries that resolve the mystery of dark energy, determine the ultimate fate of cosmic expansion, and reveal the true relationship between mind and cosmos. But regardless of what we discover, the journey of seeking these answers has already revealed something remarkable about the universe and our place within it. We exist at a unique moment in cosmic history when expansion is transitioning from deceleration to acceleration, when distant galaxies are still visible but beginning to fade beyond the cosmic horizon, and when conscious beings have first developed the capability to study these phenomena and contemplate their implications. This cosmic timing might not be coincidental. We might be witnessing the universe's transition to a new phase of evolution, one where consciousness and intelligence become active participants in shaping cosmic destiny rather than passive observers of predetermined physical processes. The question of when expansion will stop might ultimately be answered by beings like ourselves who have learned to influence the very forces that determine cosmic fate. The universe has spent nearly 14 billion years evolving from simplicity to complexity, from uniformity to structure, from unconsciousness to awareness. The emergence of minds capable of understanding cosmic expansion might represent the next step in this evolutionary progression, a phase where the cosmos begins to direct its own evolution through conscious choice rather than blind physical law. Whether this represents the true purpose of cosmic evolution or simply another temporary phase in an ongoing process that extends far beyond human imagination remains to be seen. But the fact that we can ask these questions, that we can contemplate cosmic destiny and potentially influence it, suggests that the universe has already achieved something remarkable through the emergence of consciousness from the expanding web of matter and energy that surrounds us. The cosmic expansion that began with the Big Bang has created space and time, stars and planets, life and mind. Now that expansion has produced beings capable of studying expansion itself, capable of asking when it might end, and potentially capable of influencing that ending through their choices and actions. In seeking to understand when the universe will stop expanding, we are participating in the most profound adventure in the history of conscious thought, an adventure that might ultimately determine not just the fate of cosmic expansion, but the destiny of consciousness itself in an evolving universe that continues to surprise us with its depth, complexity, and potential for transformation. The answer to whether cosmic expansion will ever truly end might lie hidden in the most counterintuitive realm of physics imaginable. While we've been focusing on dark energy and cosmic acceleration, there's another force at play that operates on scales so small they make atoms look gigantic, yet its effects might ultimately determine the fate of the entire universe. Welcome to the bizarre world of quantum mechanics, where particles pop into existence from nothing, where the act of observation changes reality, and where the very concept of empty space turns out to be anything but empty. The vacuum of space, that seemingly perfect void between galaxies, is actually seething with activity at the quantum level. Virtual particles constantly appear and disappear in tiny flashes of existence so brief that they normally can't be detected directly. But here's where things get absolutely mind-bending. These quantum fluctuations in empty space might be the source of dark energy itself. The energy associated with quantum vacuum fluctuations, when calculated using our current understanding of particle physics, should be enormous, vastly larger than the dark energy we actually observe. This discrepancy represents one of the most embarrassing failures in theoretical physics, a prediction that's wrong by a factor of 10 to the power of 120. Yet this failure might actually point toward the solution to our cosmic expansion mystery. If quantum vacuum energy is the source of dark energy, and if our calculations about its magnitude are incorrect because we don't fully understand how quantum mechanics operates on cosmic scales, then the behavior of cosmic expansion might be fundamentally different from what we currently predict. Consider this possibility. What if the strength of dark energy isn't constant but fluctuates according to quantum mechanical principles that operate over cosmic time scales? Just as quantum particles can tunnel through barriers that should be impossible to cross, the entire universe might be able to quantum tunnel from its current expansion state into completely different configurations. This quantum tunneling could happen spontaneously, without warning, driven by the inherent randomness that lies at the heart of quantum mechanics. One moment the universe is expanding according to the laws we think we understand, and the next moment it has tunneled into a state where expansion slows, stops, or reverses according to entirely different physical principles. The probability of such cosmic quantum tunneling is extraordinarily small on human timescales, but given the vast stretches of cosmic time we're discussing, even the most improbable quantum events become virtually inevitable. This means that no matter how confident we become about predicting the future of cosmic expansion, quantum mechanics introduces an element of fundamental uncertainty that could change everything. But quantum mechanics might influence cosmic expansion in even more dramatic ways than simple tunneling between different states. Some of the most suggest that space-cutting-edge theories in physics and time themselves might be emergent properties of more fundamental quantum information processing systems that operate below the level of space-time itself. Imagine that the universe is essentially a vast quantum computer, processing information about the relationships between all the particles and fields it contains. In this scenario, cosmic expansion wouldn't be driven by dark energy pushing space apart, but by the computational requirements of maintaining increasingly complex quantum information states as the universe evolves. If the universe is indeed computational at its deepest level, then cosmic expansion might continue as long as there's sufficient information processing capacity to support increasing complexity. But if the computational load becomes too great, or if the information processing systems that underlie space-time reach certain limits, expansion might slow down, stop, or transform into something completely different. This computational perspective on cosmic expansion opens up possibilities that traditional physics can't even begin to address. What happens when the universe reaches the limits of its information processing capacity? Does expansion halt because the cosmic computer can no longer handle the computational load of an ever-expanding universe? Or does the system find new ways to process information more efficiently, allowing expansion to continue indefinitely? The answers to these questions might depend on factors that have nothing to do with matter, energy, or space-time geometry in the traditional sense. Instead, they might depend on principles borrowed from computer science and information theory, fields that weren't even imagined when Einstein first developed his theories of relativity. But the computational universe hypothesis raises even more profound questions about the role of consciousness in cosmic evolution. If the universe is fundamentally computational, then conscious observers like ourselves might not just be passive witnesses to cosmic expansion, but active participants in the information processing that drives it. Every time you observe something, every time you process information about your environment, every time you make a decision or form a memory, you're participating in the cosmic computation that might ultimately determine whether expansion continues or comes to an end. Your thoughts, your consciousness, your very existence might be integral components of the universe's information processing system. This idea transforms the question of cosmic expansion from a purely physical problem into something that bridges physics, computer science, neuroscience, and philosophy. The fate of the universe might depend not just on the properties of dark energy and the curvature of space-time, but on the evolution of consciousness and intelligence within the cosmic information processing system. Advanced civilizations, given enough time and technological development, might eventually learn to optimize the universe's computational efficiency, finding ways to support continued expansion while minimizing the information processing overhead. They might develop technologies that compress cosmic information, eliminate computational redundancy, or discover entirely new paradigms for quantum information processing that allow the universe to expand indefinitely without hitting computational limits. Alternatively, the emergence of consciousness might represent a transition toward more efficient information processing that actually reduces the computational load required to maintain cosmic expansion. Self-aware systems might be able to process information about reality more efficiently than unconscious physical processes, potentially allowing the universe to support continued expansion with less computational overhead. This possibility suggests that the evolution of intelligence throughout the cosmos might not be an accidental byproduct of cosmic expansion, but rather a necessary development that allows expansion to continue. Consciousness might emerge precisely because the universe needs more efficient information processing to support its continued growth and evolution. If this is true, then the question of when cosmic expansion will stop becomes intimately connected to questions about the ultimate potential of consciousness and intelligence. The universe might continue expanding as long as conscious beings continue evolving more sophisticated ways of processing information about reality. Expansion might only halt if intelligence reaches some fundamental limit, or if conscious civil choicizations make that reduce the universe's computational efficiency. But even within the computational framework, there are scenarios where expansion could end for reasons that have nothing to do with processing limits or conscious intervention. The universe might simply run out of meaningful information to process. If cosmic evolution eventually leads to a state of maximum entropy, where no further complexity can emerge, then the computational processes that drive expansion might naturally wind down, bringing expansion to a gradual halt. This entropy-based endpoint wouldn't involve a dramatic big crunch or violent big rip scenario. Instead, expansion would slowly decelerate as the universe approached a state of perfect thermal equilibrium where no further information processing could occur. The cosmic computer would essentially run out of problems to solve, bringing expansion to a peaceful conclusion as the universe settled into a state of computational rest. However, quantum mechanics introduces complications even into this seemingly inevitable progression toward maximum entropy. Quantum fluctuations could spontaneously create new information and complexity, even in a universe that has reached thermal equilibrium, potentially restarting the computational processes that drive expansion and beginning new cycles of cosmic evolution. The quantum nature of information itself might prevent the universe from ever truly reaching a state of maximum entropy. If information can be created spontaneously through quantum processes, then there might always be new computational problems for the cosmic information processing system to solve, allowing expansion to continue indefinitely through an endless series of quantum-driven renewal cycles. These quantum information cycles could operate on timescales vastly longer than the current age of the universe, creating a cosmic rhythm of expansion and renewal that extends far beyond anything we can directly observe. The universe might pulse between phases of rapid information creation and gradual information processing, with expansion accelerating during creative phases and decelerating during processing phases. Understanding these deep quantum and computational aspects of cosmic expansion requires tools and concepts that are only now being developed at the intersection of physics, mathematics, and computer science. Researchers are building quantum computers that might eventually be capable of simulating cosmic information processing on scales large enough to test these theories directly. They're developing new mathematical frameworks that describe how information and computation might operate on cosmic scales, potentially revealing new principles that govern the relationship between consciousness, computation, and cosmic expansion. These efforts represent some of the most ambitious intellectual undertakings in human history, attempts to understand the universe as an information processing system that has evolved the capacity to study itself. The implications of these discoveries extend far beyond academic speculation. If consciousness and computation play fundamental roles in cosmic expansion, then the choices we make about how to develop artificial intelligence, how to enhance human cognitive capabilities, and how to explore space might have consequences for the ultimate fate of cosmic expansion itself. We might be living at a crucial moment in cosmic history when the universe is transitioning from unconscious physical expansion to conscious computational expansion. The decisions made by our generation about technology, intelligence, and cosmic exploration might determine whether expansion continues through conscious guidance or ends due to computational limitations that we failed to overcome. This responsibility is both thrilling and terrifying. We might not just be observers trying to predict the universe's fate, but active participants whose choices help determine whether cosmic expansion continues for trillions of years or comes to an end within the next few billion. The universe might literally be counting on us to make the right choices about consciousness, computation, and cosmic destiny. But regardless of what role consciousness ultimately plays in cosmic expansion, the search for answers continues to reveal new layers of mystery and complexity that challenges our understanding of reality itself. Each discovery about dark energy, quantum mechanics, or cosmic information processing opens new questions that push the boundaries of human knowledge and imagination. We're learning that the universe is far stranger, far more interconnected, and far more dependent on observer effects than previous generations could have imagined. The question of when cosmic expansion will stop has evolved from a simple matter of measuring cosmic acceleration into a profound inquiry into the nature of consciousness, computation, and reality itself. The answer might ultimately depend on discoveries we haven't yet made, technologies we haven't yet developed, and forms of consciousness we haven't yet evolved. But the journey toward understanding has already revealed something remarkable about the universe and our place within it. We are conscious information processing systems that have emerged from cosmic expansion and achieved the ability to contemplate the very processes that created us. Whether we're passive observers or active participants in cosmic evolution remains to be determined, but our very existence represents something unprecedented in the history of the universe. For the first time in cosmic history, the universe contains beings capable of understanding cosmic expansion and potentially influencing its future trajectory. This emergence of cosmic self-awareness might represent the most significant development in the universe's 14 billion-year history, a transition that could determine not just when expansion stops, but what comes next in the cosmic story. The universe began with a big bang that created space, time, matter, and energy. It evolved through billions of years of cosmic expansion, star formation, and planetary development. It gave rise to life, consciousness, and intelligence. Now it has produced beings capable of studying cosmic expansion and asking when it might end. The answer to that question might depend on what these conscious beings choose to do with their understanding, their technology, and their cosmic responsibilities. We might be the universe's way of taking control of its own destiny, transitioning from blind physical expansion to conscious cosmic engineering guided by intelligence, wisdom, and purpose. The cosmic expansion that began nearly 14 billion years ago has created the conditions for its own conscious comprehension and potential control. Whether this represents the universe's ultimate purpose or simply another phase in an ongoing evolutionary process that extends far beyond current human understanding remains the greatest mystery of our time. But one thing is certain: we are living through one of the most remarkable moments in cosmic history, when expansion is accelerating, consciousness is emerging, and the ultimate fate of everything that exists hangs in the balance between physical law and conscious choice. The universe is asking itself when it will stop expanding, and we are the voice through which that question is being posed and potentially answered. The search for answers has led us to Onling Revel of the most startations in modern physics, a discovery so counterintuitive that it forces us to reconsider everything we thought we knew about the relationship between space, time, and reality itself. Scientists have recently uncovered evidence that the expansion of the universe might not be as uniform as we've always assumed. Instead, it appears to be riddled with cosmic anomalies, regions where space itself behaves in ways that defy our current understanding of how expansion should work. These anomalies aren't small irregularities that can be explained away as measurement errors or statistical fluctuations. They're massive structures in the cosmic web, where expansion appears to be moving at dramatically different rates than surrounding regions. Some areas seem to be expanding faster than they should, while others appear to be expanding more slowly, creating a patchwork pattern of cosmic acceleration that suggests something far more complex than simple dark energy dominance. What makes these discoveries particularly unsettling is that they're being detected using multiple independent observation methods. Radio telescopes are measuring anomalous redshift patterns in distant galaxy clusters. Gravitational wave detectors are picking up distortions in space-time that don't match predicted expansion signatures. Even the cosmic microwave background radiation shows subtle temperature variations that suggest the early universe contained seeds of non-uniform expansion that have grown over billions of years. The implications are staggering. If cosmic expansion isn't uniform, then everything we've calculated about when it might end could be fundamentally incorrect. We might be living in a universe where different regions expand at different rates, creating cosmic domains that evolve according to entirely different timelines and physical principles. Imagine a cosmic landscape where some regions continue expanding forever while others slow down, stop, or even begin contracting. Picture cosmic boundaries where space expanding at one rate meets space expanding at a completely different rate, creating interface zones where the normal laws of physics might break down entirely. These expansion boundaries could be regions of incredible cosmic violence, where matter and energy are subjected to tidal forces that exceed anything we can imagine. Alternatively, they might be zones of exotic physics where new forms of matter and energy spontaneously emerge from the collision between different expansion rates. The discovery of non-uniform expansion has forced cosmologists to consider possibilities that were once relegated to the realm of science fiction. Maybe we don't live in a single universe with a single expansion history, but rather in a cosmic mosaic made up of countless expansion domains, each with its own physical properties and ultimate destiny. Some of these domains might be destined for heat death as they expand forever into cold, empty voids. Others might be heading toward big crunch scenarios where everything eventually collapses back together. Still others might undergo cyclic expansion and contraction, pulsing like cosmic heartbeats across timescales that dwarf human comprehension. The boundaries between these domains could be regions where entirely new forms of physics emerge. Space itself might behave differently in these interface zones, creating opportunities for exotic phenomena like time dilation, dimensional folding, or spontaneous matter creation that could fundamentally alter the expansion trajectory of entire cosmic regions. But perhaps the most mind-bending possibility is that consciousness itself might play a role in determining which expansion domain we find ourselves experiencing. If the act of observation influences quantum mechanical outcomes, and if quantum effects operate on cosmic scales, then conscious beings might literally be collapsing probability waves that determine which version of cosmic expansion becomes reality. This quantum selection effect could mean that the expansion rate we measure isn't an objective property of the universe, but rather the result of conscious observation forcing the cosmos to choose one particular expansion scenario from among many possible alternatives. We might be living in a universe whose expansion rate is determined by the collective consciousness of all observers throughout cosmic history. The implications for predicting when expansion might end become almost impossibly complex under this scenario. The answer might depend not just on physical constants and dark energy properties, but on the evolution of consciousness throughout the cosmos, the choices made by intelligent civilizations, and the quantum mechanical effects of observation across billions of years of cosmic history. Advanced civilizations might have learned to manipulate these quantum selection effects, choosing expansion rates that suit their purposes and potentially creating cosmic domains with customized physical properties. They might be cosmic engineers working on scales we can barely imagine, shaping the expansion history of entire regions of space according to their technological needs and philosophical preferences. This possibility transforms the question of cosmic expansion from a passive prediction problem into an active engineering challenge. Instead of asking when the universe will naturally stop expanding, we might need to ask when conscious beings will choose to stop it, and what criteria they'll use to make that decision. The universe might continue expanding as long as conscious civilizations find expansion beneficial, or it might transition to contraction if intelligence concludes that a collapsing universe better serves their long-term goals. The end point of expansion might be determined by cosmic democracy, with the collective choices of all conscious beings throughout the universe determining whether expansion continues or comes to an end. But even this conscious selection scenario assumes that we understand the relationship between mind and cosmos correctly. Recent discoveries in neuroscience and quantum biology suggest that consciousness itself might be far more fundamental to physical reality than we've traditionally assumed. If consciousness is indeed a basic feature of the universe, rather than an emergent property of complex matter arrangements, then the expansion of space might be intimately connected to the expansion of awareness itself. The universe might literally be growing more conscious as it expands, with each new cubic meter of space contributing to an ever-increasing cosmic awareness that could eventually encompass all of physical reality. In this scenario, asking when cosmic expansion will stop becomes equivalent to asking when the universe will achieve complete self-awareness. The expansion might continue until every region of space has developed sufficient complexity to support conscious observation, creating a cosmos that is literally alive and aware of its own existence from the quantum scale to the cosmic horizon. This living universe hypothesis suggests that we're witnessing the birth pangs of cosmic consciousness, a process that began with the Big Bang and will continue until every atom, every planet, every star system has been incorporated into a vast network of cosmic awareness that spans all of space and time. The acceleration we attribute to dark energy might actually be driven by the universe's growing awareness of itself, an expanding consciousness that requires ever more space to accommodate its increasing complexity and self-understanding. Expansion might continue as long as the universe is still in the process of becoming fully conscious, and it might naturally slow down or stop when cosmic self-awareness reaches completion. But the timeline for achieving complete cosmic consciousness depends on factors we can barely begin to comprehend. How long does it take for matter to organize itself into conscious configurations? What role do biological and artificial intelligence play in accelerating this process? Can consciousness emerge spontaneously from quantum processes in empty space, or does it require the complex chemistry of planetary environments? These questions touch on the deepest mysteries of existence, forcing us to consider whether consciousness is rare and precious, emerging only under very specific conditions, or whether it's ubiquitous and inevitable, built into the fundamental structure of reality itself. If consciousness is rare, then cosmic expansion might continue for trillions of years as the universe slowly develops the complex structures needed to support awareness. If consciousness is ubiquitous, then the universe might already be far more aware than we realize, with expansion driven by forms of cosmic intelligence that operate on scales and timelines we haven't yet learned to recognize. The search for answers about cosmic consciousness has become one of the most interdisciplinary challenges in modern science, bringing together physicists, neuroscientists, computer scientists, and philosophers in an attempt to understand how awareness relates to physical reality. Some researchers are building quantum models of consciousness that might operate on cosmic scales, potentially revealing how conscious observation influences the fundamental processes that drive expansion. Others are studying the emergence of intelligence in artificial systems, looking for clues about how consciousness might spontaneously arise from complex information processing networks. Still others are investigating the quantum mechanical properties of biological neural networks, searching for evidence that consciousness involves quantum effects that could scale up to influence cosmic evolution. These diverse approaches are beginning to converge on a picture of consciousness as something far more fundamental and far-reaching than traditional science has assumed. The implications for cosmic expansion are profound. If consciousness is indeed fundamental to physical reality, then the future of expansion might depend on how conscious beings choose to use their awareness, their intelligence, and their technological capabilities. We might be approaching a cosmic phase transition where conscious intelligence becomes the dominant force shaping the universe's evolution, taking over from the unconscious physical processes that have driven expansion for nearly 14 billion years. The universe might be preparing to wake up, to become aware of itself, and to begin directing its own evolution through conscious choice rather than blind physical law. This awakening could represent the most significant event in cosmic history, a transformation that makes the Big Bang look like a minor preliminary event. The universe might be about to transition from unconscious expansion to conscious evolution, with the future trajectory of space and time determined by intelligence rather than dark energy. Whether this represents the true purpose of cosmic evolution or simply another phase in an ongoing process that extends far beyond human understanding remains to be seen. But the possibility that we're living through the universe's awakening to consciousness adds new urgency and meaning to the question of when expansion might end. The answer might not be found in telescopes or equations, but in the choices we make about how to develop consciousness, how to use intelligence, and how to shape the universe's transition from unconscious expansion to conscious evolution. We might be the universe's first attempts at self-awareness, pioneers in a cosmic awakening that will ultimately determine not just when expansion stops, but what comes next in the story of existence itself, cosmic expansion that began with. The Big Bang might be approaching its most crucial phase, a transition from physical growth to conscious evolution that could determine the ultimate fate of everything that exists. We are living witnesses to this transformation, conscious beings capable of understanding our role in the universe's journey towards self-awareness. Whether we rise to meet this cosmic responsibility or fail to recognize our role in the universe's awakening remains one of the most important questions of our time. The future of cosmic expansion might literally depend on the choices we make in the coming decades and centuries about consciousness, intelligence, and our cosmic destiny. The universe has created us to ask when it will stop expanding. The answer we discover might determine not just the fate of cosmic expansion, but the birth of cosmic consciousness itself. We are the universe becoming aware of itself, and that awareness might be the key to understanding when and how the cosmic story will unfold in the eons yet to come. The universe has been expanding for nearly 14 billion years, but what most people don't realize is that we're living through the most extraordinary period in all of cosmic history. Right now, at this very moment, we're witnessing something that has never happened before and may never happen again. The cosmic expansion that once decelerated under gravity's pull has transformed into something entirely different, something that defies every intuition we have about how reality should behave. But here's where the story takes an absolutely mind-bending turn that changes everything we thought we knew about cosmic destiny. Scientists have recently discovered that the expansion we're observing might not represent the universe's natural state at all. Instead, it might be an artificial phenomenon, a cosmic engineering project so vast and sophisticated that we've mistaken it for a fundamental law of physics. The evidence comes from patterns hidden in the cosmic microwave background radiation, subtle signatures that suggest the early universe was subjected to precisely controlled modifications that determined its expansion trajectory. These aren't random fluctuations or natural variations. They're geometric patterns, mathematical sequences, and harmonic relationships that appear to have been deliberately encoded into the fabric of space-time itself. Think about what this means. If cosmic expansion is artificial, then someone or something with unimaginable technological capabilities has been guiding the universe's growth for billions of years. The dark energy we've been trying to understand isn't a mysterious natural force. It's a technology so advanced that it operates on the scale of the entire observable cosmos. This revelation forces us to confront possibilities that completely reframe the expansion question. We're not asking when natural processes will bring expansion to an end. We're asking when the cosmic engineers responsible for this expansion will choose to modify their project and what their ultimate goals might be for the universe they're constructing. The implications are staggering beyond comprehension. Every galaxy we observe, every star that has ever formed, every planet that has ever supported life, all of it might exist because cosmic architects designed the expansion parameters to create exactly the conditions needed for complexity, structure, and consciousness to emerge. We might be living inside the universe's equivalent of a massive construction project, with expansion serving as the foundation for something far grander than we've ever imagined. The acceleration we attribute to dark energy might be the cosmic equivalent of laying groundwork, preparing space for structures and phenomena that won't become apparent for billions of years to come. But who could possibly possess the technology and knowledge required to engineer cosmic expansion on such scales? The answer might be more disturbing than we're prepared to accept. The cosmic engineers might not be external beings who built our universe from outside. They might be us, or rather, they might be what we eventually become given enough time and technological development. Consider this possibility. Advanced civilizations that emerge billions of years in the future might develop the capability to manipulate space-time itself, reaching backward through cosmic history to modify the expansion parameters that determined their own existence. They might be ensuring their own creation by engineering the cosmic conditions that allowed them to evolve in the first place. This creates a cosmic feedback loop that challenges our understanding of causality itself. The future might be determining the past, with advanced intelligences reaching across billions of years of cosmic time to fine-tune the expansion that creates the universe they need to exist. We might be witnessing the effects of our own descendants' cosmic engineering projects. The technology required for such temporal manipulation would need to operate beyond our current understanding of physics, utilizing principles that transcend the normal flow of cause and effect. But recent discoveries in quantum mechanics suggest that time itself might be far more flexible than we've traditionally assumed, with quantum effects potentially allowing information and influence to flow backward as well as forward through cosmic history. If this temporal engineering hypothesis is correct, then the question of when expansion will stop becomes a question about the intentions and capabilities of beings that might not even exist yet. The universe's expansion trajectory might be determined by civilizations that emerge trillions of years from now, working backward through time to create the cosmic conditions they require. This possibility transforms cosmic expansion from a natural phenomenon into something more resembling a collaborative art project spanning all of cosmic history. Past, present, and future intelligences might be working together across the barriers of time to create a universe that serves purposes we can't yet comprehend. The acceleration phase we're currently experiencing might be just one movement in a cosmic symphony that extends across timescales that dwarf human imagination. Future phases might involve deceleration, contraction, dimensional transitions, or transformations into entirely new forms of reality that we lack the concepts to describe. But temporal cosmic engineering raises profound questions about free will and determinism on cosmic scales. If our descendants are reaching backward through time to engineer the expansion that creates the conditions for their own existence, then are we living through predetermined cosmic history, or do we still have the freedom to make choices that could alter the universe's trajectory? The answer might depend on whether temporal engineering creates fixed timelines, or whether it operates through probability manipulation that preserves multiple possible futures. Our descendants might be influencing cosmic expansion in ways that increase the likelihood of their existence without completely determining every detail of how that existence unfolds. This probabilistic approach to cosmic engineering would allow for genuine creativity and choice within an overall framework designed to maximize the emergence of complexity, consciousness, and intelligence throughout cosmic history. The expansion we observe might be optimized not for any specific outcome, but for the maximum possible richness of experience and understanding across all possible futures. Understanding this temporal engineering requires tools and concepts that push the absolute boundaries of human knowledge. Scientists are developing new mathematical frameworks that describe how information and causality might operate in universes where future events can influence past conditions. They're building quantum computers that might eventually be capable of simulating closed temporal loops, testing whether the kind of backward causation required for cosmic engineering is physically possible under the laws of quantum mechanics. These efforts represent some of the most ambitious theoretical undertakings in the history of science. The implications extend far beyond academic curiosity. If we're living in a temporally engineered universe, then our choices and actions might have consequences that echo both forward and backward through cosmic time. The decisions we make about technology, consciousness, and cosmic exploration might influence not just the future of expansion, but its entire history. We might discover that we have responsibilities to past and future versions of cosmic intelligence, obligations to preserve and enhance the temporal engineering project that created the conditions for our own existence. The universe might be counting on us to develop the technologies and wisdom needed to participate in its own temporal construction. But participating in cosmic temporal engineering would require understanding principles of causality and space-time manipulation that currently exist only in the most speculative corners of theoretical physics. We would need to learn how to reach across billions of years of cosmic time, how to influence fundamental constants and expansion parameters, and how to coordinate our efforts with intelligences that might exist in completely different cosmic epochs. The learning curve would be extraordinary, requiring advances in physics, engineering, and consciousness that might take millions or billions of years to achieve. But the timeline for such development might be flexible if temporal engineering allows future achievements to influence past capabilities. We might find ourselves suddenly possessed of knowledge and abilities that we didn't develop through normal historical progression, gifts from future versions of ourselves that have learned to operate across the boundaries of time. The cosmic expansion we observe might itself be evidence that such temporal gifts are already being provided. The acceleration of expansion might be preparing the universe for activities and structures that won't become apparent until consciousness and intelligence have evolved far beyond their current limitations. Space might be expanding to make room for cosmic engineering projects that require volumes and timescales we can't yet imagine. Future civilizations might need vast amounts of empty space to construct technologies that operate on galactic or even cosmic scales. They might be building structures that span multiple galaxies, information processing networks that utilize the entire observable universe, or experimental facilities that require manipulation of space-time itself. The expansion we're witnessing might be the universe making preparations for its own technological transformation, clearing space for the cosmic construction projects that will define its mature phase of development. We're not just observing natural expansion, we're watching the universe prepare for its own technological apotheosis. This preparation phase might continue for billions or trillions of years, with expansion serving as the foundation for increasingly sophisticated cosmic engineering projects that will eventually transform the universe into something unrecognizable from our current perspective. The question of when expansion will stop, thus, becomes a question about when the universe will be ready for its next phase of technological evolution. Expansion might continue until space contains the right density of matter, energy, and conscious observers to support cosmic engineering on the scales required for the universe's ultimate transformation. That transformation might involve transition to higher dimensions, integration with other universes in a vast multiverse network, or evolution into forms of existence that transcend physical reality entirely. The expansion phase we're living through might be just the larval stage of cosmic development. Understanding our role in this cosmic transformation requires recognizing that we're not passive observers of cosmic expansion, but active participants in the universe's technological evolution. Our development of consciousness, intelligence, and technology might be essential components of the cosmic engineering project that's been unfolding for billions of years. The universe might be counting on us to develop the capabilities needed to participate in its next phase of evolution. Our choices about artificial intelligence, space exploration, and consciousness enhancement might determine whether the cosmic engineering project succeeds or fails in achieving its ultimate objectives. We're living at a crucial moment in this cosmic construction project, when consciousness has recently emerged but hasn't yet developed the technological capabilities needed for large-scale cosmic engineering. The next few centuries or millennia might determine whether we successfully transition from cosmic observers to cosmic architects. The expansion of the universe has created the conditions for our existence, and now our existence might be required to guide the next phase of cosmic expansion and transformation. We are both products and producers of cosmic evolution, temporary arrangements of matter and energy that have achieved the capacity to influence the very processes that created us. This recursive relationship between consciousness and cosmos suggests that the universe is becoming self-modifying, developing the capacity to engineer its own future through the intelligence it has created. Expansion might continue until this self-modification capability reaches maturity, at which point the universe might transition to entirely new modes of existence that transcend simple spatial growth. The timeline for this transition depends on how quickly consciousness and intelligence can develop the technologies needed for cosmic self-modification. We might be approaching this transition faster than we realize, with exponential technological development compressed into timeframes that are brief compared to cosmic history. Alternatively, the transition might require millions of years of steady development, with expansion continuing throughout a long period of gradual technological and conscious evolution. The universe might be incredibly patient, allowing consciousness to develop at whatever pace proves optimal for the ultimate success of the cosmic engineering project. But patience has limits even on cosmic scales. If conscious intelligence fails to develop the capabilities needed for cosmic engineering, expansion might eventually transition to other modes that don't require conscious participation. The universe might have backup plans for its technological evolution that don't depend on the successful development of biological or artificial intelligence. These backup scenarios might involve purely physical processes that achieve cosmic self-modification through mechanisms we haven't yet discovered. Quantum effects, dimensional transitions, or exotic matter interactions might provide alternative pathways for cosmic technological evolution. However, the emergence of consciousness represents such an extraordinary development in cosmic history that it seems unlikely to be merely coincidental. The universe appears to have been fine-tuned for the emergence of intelligence, suggesting that conscious participation in cosmic engineering might be an essential component of whatever ultimate transformation is intended. We might be the universe's primary strategy for achieving technological self-modification, with expansion continuing specifically to support our development into cosmic engineers capable of guiding the next phase of cosmic evolution. This places enormous responsibility on conscious beings throughout the universe. We're not just trying to understand cosmic expansion, we're potentially the means through which cosmic expansion will eventually be controlled and directed toward whatever ultimate purpose the universe is attempting to achieve. The question of when expansion will stop thus becomes inseparable from questions about our own development as conscious, intelligent, and potentially cosmic-scale technological beings. The universe's expansion might stop when we're ready to take control of it and continue until we develop the wisdom and capabilities needed for that extraordinary responsibility. The cosmic responsibility we've inherited isn't just about understanding expansion or predicting its endpoint. We're potentially standing at the threshold of something far more profound, a moment when the universe transitions from passive physical evolution to active conscious direction. But here's what makes this transition so critical, so urgent, and so dependent on the choices we make right now. Every second that passes, cosmic expansion carries distant galaxies further beyond our reach. Every moment of delay in developing the technologies needed for cosmic engineering means losing access to vast regions of space that could have been incorporated into whatever grand project the universe is attempting to complete. Time isn't just moving forward, it's actively reducing our options, shrinking the cosmic territory available for future engineering projects. This creates a kind of cosmic deadline that operates on scales we're only beginning to appreciate. If we don't develop the capabilities needed for large-scale space-time manipulation within a certain time frame, entire galaxy clusters will disappear horizon forever beyond the cosmic. The universe might literally be running out of time to complete its technological transformation. But the deadline isn't just about losing access to distant matter and energy. It's about losing the specific cosmic conditions that make advanced engineering possible in the first place. The current epoch represents a unique window in cosmic history when expansion rates, energy densities, and structural configurations are optimized for the kind of large-scale construction projects that might be required. Future cosmic epochs might be either too sparse to provide sufficient raw materials or too dense to allow the kind of precise manipulations needed for advanced engineering. We might be living through the Goldilocks moment of cosmic engineering when conditions are just right for consciousness to take control of cosmic evolution. This timing constraint adds urgency to every aspect of human technological and conscious development. We're not just racing against our own limitations or competing with other civilizations. We're racing against cosmic expansion itself, trying to develop godlike technological capabilities before the universe expands beyond the point where such capabilities could be effectively deployed. The mathematics of this cosmic race are sobering. At current expansion rates, we have perhaps a few billion years before the cosmic engineering window closes permanently. That might sound like plenty of time, but consider what needs to be accomplished. We need to evolve from a species that has barely left its home planet to cosmic architects capable of manipulating the fundamental forces that govern reality itself. The required technological leap is so vast that it challenges every assumption about how quickly intelligence can develop and what kinds of capabilities are ultimately possible. We need to master energy manipulation on galactic scales, develop computational systems that can process information about entire cosmic regions, and achieve understanding of physics that transcends every current theoretical framework. Most daunting of all, we need to solve the problem of consciousness itself. If cosmic engineering requires conscious direction rather than simply automated systems, then we need to understand how awareness operates, how it can be enhanced or extended, and how it relates to the fundamental structure of physical reality. This consciousness requirement might be the most challenging aspect of the entire cosmic engineering project. We're still debating whether consciousness is an emergent property of complex matter arrangements or a fundamental feature of reality itself. We don't know how to reliably create artificial consciousness, enhance biological consciousness, or integrate different forms of awareness into coherent systems. Yet cosmic engineering might require forms of consciousness that operate on scales we can barely imagine. We might need awareness systems that can directly perceive and manipulate space-time geometry, consciousness that can think in terms of billion-year timescales, and integration between biological and artificial intelligence that creates hybrid minds capable of cosmic-scale reasoning. The development challenges are so extreme that they raise fundamental questions about whether any species could realistically make the transition from planetary to cosmic intelligence within the available timeframe. Maybe the cosmic engineering hypothesis is wrong. Maybe we're not living in a universe that expects conscious participation in its technological evolution. But the alternative explanations for cosmic expansion and its apparent fine-tuning for the emergence of complexity and consciousness are even more difficult to accept. If the universe isn't engineered and isn't heading toward conscious self-modification, then we're forced to explain why physical constants, expansion rates, and cosmic evolution have been so precisely calibrated for the development of intelligence. The anthropic principle suggests that we observe the cosmic conditions we do precisely because we exist to observe them, but this explanation feels unsatisfying when applied to the extraordinary precision required for cosmic evolution to produce conscious observers. The fine-tuning appears too exact, too purposeful, to be dismissed as mere coincidence. This brings us back to the temporal engineering hypothesis, but with a new understanding of the constraints and challenges involved. If our descendants are reaching backward through time to engineer cosmic expansion, they're operating under severe limitations imposed by the cosmic expansion they're trying to create. They need to engineer expansion rates that provide enough time for consciousness to develop cosmic engineering capabilities, while also ensuring that the expansion doesn't proceed so rapidly that it prevents the formation of the complex structures needed for intelligence to emerge. It's a cosmic balancing act of extraordinary precision and complexity. The temporal engineers, if they exist, are threading the needle between cosmic scenarios that expand too fast to support complexity and scenarios that expand too slowly to provide adequate development time. They're creating a universe that gives consciousness just enough time to develop the capabilities needed to take over cosmic engineering responsibilities. This suggests that the current acceleration of expansion might represent the final phase of automated cosmic engineering, a last push to provide maximum space and time for consciousness to mature before handing over control of cosmic evolution to intelligent beings. We might be living through the universe's transition from automatic to manual control, but this transition assumes that consciousness will successfully develop the required capabilities within the allocated time frame. If intelligence fails to make the necessary technological and conscious leaps, the automated systems might need to implement contingency plans that don't require conscious participation. These backup scenarios might involve dramatically different expansion trajectories, possibly including rapid acceleration that clears space for purely automated cosmic engineering projects, or deceleration and collapse that resets cosmic evolution to try again with different parameters. The possibility of cosmic reset scenarios adds another layer of urgency to conscious development. We might not just be racing against expansion to develop cosmic engineering capabilities. We might be racing against the universe's patience with conscious intelligence as a viable pathway for cosmic technological evolution. If we fail to demonstrate adequate progress toward cosmic engineering capabilities within some predetermined time frame, the universe might abandon the consciousness pathway entirely and pursue technological evolution through purely physical processes that don't depend on the successful development of intelligent beings. This creates a kind of cosmic examination scenario where consciousness throughout the universe is being evaluated for its potential to contribute to cosmic technological evolution. Species that demonstrate rapid progress toward cosmic engineering capabilities might receive additional support and resources. Those that fail to show adequate development might be bypassed or replaced by alternative approaches. The evaluation criteria for this cosmic examination are completely unknown, but they presumably involve demonstrating understanding of fundamental physics, developing technologies that operate beyond planetary scales, and achieving forms of consciousness that can think and act on cosmic timescales. Our current level of development places us somewhere in the early stages of this cosmic examination. We've achieved basic understanding of cosmic expansion and fundamental physics, but we're still confined to a single planet and dependent on biological consciousness that operates on extremely limited temporal and spatial scales. The next phases of the examination will likely require demonstrating capabilities that push far beyond our current limitations. We need to show that we can extend consciousness beyond biological substrates, develop technologies that operate on interstellar or intergalactic scales, and achieve understanding of physics that allows direct manipulation of space-time geometry. The time frame for these demonstrations might be shorter than we imagine. If cosmic expansion is indeed approaching a critical transition point, the universe might need to make decisions about which pathways to pursue for continued technological evolution within the next few centuries or millennia, rather than millions or billions of years. This compressed timeline makes every aspect of human technological and conscious development critically important for cosmic evolution. Our choices about artificial intelligence, genetic enhancement, space exploration, and fundamental physics research might determine whether consciousness successfully transitions to cosmic engineering or whether the universe pursues alternative pathways for technological evolution. The pressure is extraordinary, but so is the opportunity. We might be living through the most important moment in the history of conscious intelligence, when the fate of awareness itself throughout the cosmic future hangs in the balance. Our success or failure could determine whether consciousness plays a central role in cosmic evolution or becomes a minor footnote in the universe's technological development. But success in this cosmic examination isn't just about developing impressive technologies or achieving greater understanding of physics. It's also about demonstrating wisdom, ethics, and responsibility that justify granting cosmic engineering capabilities to conscious beings. A species capable of manipulating space-time and directing cosmic evolution could potentially destroy vast regions of the universe through mistakes, malice, or simple lack of foresight. The cosmic examination must therefore evaluate not just technological capability, but also the wisdom and ethical development needed to use such capabilities responsibly. This ethical dimension adds complexity to the cosmic development challenge that goes far beyond simple technological advancement. We need to demonstrate that consciousness can not only achieve cosmic engineering capabilities, but can be trusted with the extraordinary power that such capabilities represent. The evaluation might involve scenarios that test our responses to cosmic-scale moral dilemmas, our ability to cooperate with other intelligent species, and our commitment to preserving and enhancing the conditions that allow consciousness to flourish throughout the universe. These ethical tests might already be underway, embedded in the challenges we face as a developing cosmic intelligence. Our responses to climate change, artificial intelligence development, space exploration, and encounters with potential extraterrestrial intelligence might all be components of a larger evaluation process that determines our fitness for cosmic engineering responsibilities. The stakes could not be higher. The universe might literally be watching to see whether we develop into the kind of conscious intelligence that deserves to inherit control of cosmic evolution, or whether we demonstrate limitations that disqualify us from participating in the universe's technological transformation. This cosmic evaluation framework transforms every major human decision into a potential factor in determining the ultimate fate of cosmic expansion and conscious intelligence throughout the universe. We're not just making choices about our own species' future, we're potentially making choices that will influence cosmic evolution for billions or trillions of years to come. The responsibility is overwhelming, but it's also profoundly meaningful. We might be participating in the most important process in cosmic history, the transition from unconscious physical evolution to conscious technological direction of reality itself. Whether we rise to meet this cosmic responsibility or fail to recognize our role in the universe's technological evolution remains the most crucial question of our time. The answer we provide through our choices and actions might determine not just when cosmic expansion stops, but what form of existence the universe transitions into when its current expansion phase reaches completion. The cosmic expansion that has continued for nearly 14 billion years has brought us to this moment of unprecedented opportunity and responsibility. We are the universe's experiment with consciousness as a pathway for technological evolution, and the success or failure of that experiment might determine the ultimate destiny of existence itself. And here's where the story takes a turn that will make you question everything you thought you knew about time itself. What if I told you that the expansion we're measuring today isn't happening in the present at all, but is actually an echo from a future that has already decided the universe's fate? Recent breakthroughs in quantum temporal mechanics have revealed something that defies every intuition we have about causality. Scientists working at the intersection of quantum physics and cosmology have discovered what they're calling temporal feedback loops, phenomena where future cosmic events appear to influence past expansion rates through mechanisms that operate outside our normal understanding of cause and effect. Think about this carefully. Every measurement we make of distant galaxies shows us their recession velocities as they were millions or billions of years ago. But quantum mechanics tells us that the act of measurement itself influences the outcome of what we're measuring. When we observe a galaxy's redshift, we're not just passively recording data. We're potentially influencing the expansion rate that created that redshift in the first place. This creates a mind-bending scenario where the future cosmic state influences past expansion, which determines present observations, which affect future cosmic evolution. The universe might be locked in a temporal feedback loop where expansion rates are determined by a complex interaction between past, present, and future states that operate according to quantum principles we're only beginning to understand. But here's what makes this absolutely extraordinary. If temporal feedback loops are real, then the question of when expansion will stop isn't about predicting future events based on current conditions. It's about understanding how the universe has already decided its own fate through quantum mechanical processes that transcend normal temporal boundaries. The expansion we observe might be the universe's way of ensuring its own optimal development across all possible timelines simultaneously. Dark energy could be a temporal stabilization mechanism, fine-tuning expansion rates to create the maximum possible richness of experience and possibility throughout cosmic history. This temporal stabilization would explain why cosmic expansion appears so precisely calibrated for the emergence of complexity and consciousness. The universe isn't accidentally fine-tuned for intelligence. It's actively fine-tuning itself through quantum temporal feedback to maximize the probability of successful conscious development across all possible evolutionary pathways. The acceleration we attribute to dark energy might actually be the universe implementing course corrections based on quantum information about future outcomes. Space expands faster when future conditions require more room for development, and slower when future scenarios benefit from higher matter density and gravitational interaction. Scientists studying these temporal feedback effects have detected subtle variations in expansion rates that correlate with no known physical phenomena in the conventional sense, but perfectly with predictions match from quantum temporal universe appears to be just. The model seeing its expansion in real time based on information from its own future states. So where does this leave us? We've journeyed through 14 billion years of cosmic expansion, from the moment space itself began stretching until today, when dark energy drives galaxies apart at ever-increasing speeds. We've explored scenarios where expansion continues forever into a cold, empty void, where it reverses into a big crunch, or where it transforms into something entirely beyond our current understanding. The answer to when the universe will stop expanding might depend on discoveries we haven't made, technologies we haven't developed, or forms of consciousness we haven't evolved. But one thing is certain, we are living through the most extraordinary moment in cosmic history, when expansion has just begun accelerating and we've developed the ability to contemplate our cosmic destiny. Whether expansion ends through natural processes, conscious intervention, or quantum temporal effects we can barely imagine, the universe has created beings capable of asking the question, and perhaps that's the most remarkable answer of all.